In this video, I introduce vector quantization GAN for high-resolution image synthesis. Transformer learns long-range interactions on sequential data. However, it contains no inductive bias that prioritizes local interactions like convolutional operations. The performance of a transformer is achieved by training on large-scale datasets due to using small kernel, for example, 3 by 3 in convolutions. CNN costs are linearly increasing with his input sequence length. However, transformer models interactions between his input solid through attention, which result in computational costs that increase quadratically with input image resolution. Attention of the input image is computed by using this formulation, where Q key, V or query key and value respectively, that are generated by using matrices WQ, W key, and WV on the input image. This architecture of a transformer model, this self-attention module. A codebook with entries ZQ is learned to represent any image X. To learn to represent images with codes from a learned discrete codebook, Z, encoder E, and decoder G are combined to optimize the latent representations of images. Reconstruction of input image X is indicated as X caret, where ZQ is obtained by first using the encoder E, and then each spatial representation ZIG caret is projected onto the closest code in the codebook, as shown here and here in this figure. Since the quantization is non-differentiable, the derivative of ZQ is used to approximate the derivative of Z caret as shown here, namely straight through gradient as shown here. The VQ loss L is defined as here, which includes three terms, namely reconstruct loss, codebook loss, and commitment loss. VQ-GAN uses discriminator and perceptual loss to keep good perceptual quality at increased compression rate. The discriminator differentiates between the real and the reconstructed images, as shown here. The overall objective for optimizing compression model Q asterisk is defined as here, which includes two terms. One is VQ loss, one is GAN loss. Whereas adaptive weight lambda is computed by using this equation, where LREC is a perceptual loss. This derivative is a gradient of his input with respect to the layer L of the decoder. This is the architecture of VQ-GAN model, this transformer that is used to learn the codebook, and this encoder, this decoder is used to learn the latent representation of the input image, this discriminator to further compress the input image. The quanta is the encoding of image X is given by ZQ. Transformer is applied to learn the quantization ZQ through a sequence S as shown here. That corresponds to the codes in the codebook. The sequence S is obtained by using this equation as shown here. This input image, this one region SIG, and this transformer is used to learn the 1D sequence S, and then the 1D sequence S is mapped to a 2D quantization for reconstruction. By mapping indices of sequence S back to their corresponding codebook entries, the image x caret is reconstructed from ZQ. Using the known indices S, the transformer learns to predict the distribution by maximizing probability of next index, and then the likelihood of the joint distribution P. The log likelihood of the distribution is maximized by using this equation. For more details, please check with these references. Thank you. Bye.